Welcome to day 17 of the macOS and iOS Security Internals Advent Calendar. Today we will be looking at Mach ports, what they are and how you use them. So first of all, a Mach port is basically a multi-purpose data structure within the kernel known as IPC_port_T. They have multiple different purposes. For example, they are used as a handle to resources or services. They are used for communication between different parties, so you can send and receive messages. And they're also used to represent capabilities that the owner has by having them. So the data structure has quite many fields in it. As you can see here, this is the first part of it. It's quite complicated data structure with a lot of flags these days. Important here, for example, is that we have more information about the port in the first IPC object field, and then each port has a message queue for receiving multiple messages. And then when you look at the rest of the structure, it looks very complicated, and depending on what kind of port we're dealing with, different fields of this structure are actually used. When you look at it, you can also see that these days a lot of the pointers inside here are actually pack protected. You can also see that not all pointers are theoretically pack protected, but many are. So let's drill down into the smaller objects. So the IPC object T structure that was in the beginning, what is that? It's basically a reference counter and a bits description that controls a little bit more about what we want to see inside the specific port. When we look at the definition of the bits, we will see that the bits are basically a bit field where you can see the highest bit specifies if a port is active or not, and the lowest 10 bits specify if it's a kernel object and what kind of kernel object it is. The kernel object can also optionally have a label here, and yeah, the rest of the stuff is not so important right now. So basically the kernel object type and the active bit are the most important fields here within the bits. So when we speak about ports, there's usually a confusion between people coming from user land and people coming from kernel land, because a port is technically just the kernel data structure, the IPC port T, or maybe a pointer to it. But in user land we don't have this kind of data structure. In user land we have something called a port name. But for many people, when they talk about ports in user land, what they actually mean are port names. So what is a port name? A port name is basically a 32-bit number that represents a user space handle to the port. And the 32-bit numbers is split into two fields. The lower 8 bits are the so-called generation count, and then the upper bits are an index into the IPC table of the task. So when you look at port names, they are basically for ports what the file descriptor is for a file. So it means the access is limited to the current task, because when it's an entry in our IPC table, we are the only task having this IPC table. So this means that nobody else has the same index in their table, and so this index has only a meaning for us. Yes, and it also makes clear that a task can only access a certain port if they have an entry in the IPC table that points to that specific port. Yeah, and the IPC table also tracks what kind of writes we have towards these ports. What I didn't get into yet was what is this generation count that is mentioned above. So the generation count is basically a protection by Apple against accidental port index reuse. Because if we only have an index like 1, 2, 3, 4, 5 or so, what happens is that when a port slot is cleared later on and another port takes its space, it would have the same index again, and Apple doesn't want that accidentally, when we talk about a specific port index, we accidentally reuse something that was closed in between and then later opened again. It's kind of like a protection against use after free. Yeah, so what is this generation count? It's basically a number that follows a kernel determined algorithm, and every time we basically reuse a port index, this generation count gets not increased. It's basically not following a linear pattern. It's more like it's moving into the next generation, you can say. So there's an algorithm that always gives you the next value for the generation count. And so basically in userland, the generation count plus the index together give you the actual user space handle for a port. So this following graphic visualizes this a little bit more, how this all comes together. So basically we have our task. Our task has an IPC space. The IPC space points to our IPC entry table, and then each entry is basically a collection of a pointer to a port, the index that this port represents, and the generation count for that index, and the writes for this port that our task has. And then the index and the gen count together represent the Mach port name in userland. So when an entry is filled, it will point to an IPC port, and the IPC port will always point to basically its so-called receiver, and the receiver is basically the IPC space of the kernel that owns the IPC space of the owner of the port. So whoever created this port and holds the so-called receive right on it. And yes, so this is the owner, and then the IPC space has a forward and back pointer to the task. So this points to the task who is the owner of this port. This could be, for example, the kernel task. This could be any other task, but it could also be the actual task that we are currently dealing with, because the port could actually be owned by this task. So in some cases, if a port represents a kernel object, then this here will point to an actual kernel object, depending on what kind of kernel object type it is. So the IPC space, in the case of a kernel object, is the IPC space of the kernel, and in this case it also points to the kernel task in this case. Yes. So let's look a little bit more at the usage. So the first usage for Mach ports is basically using them as a handle to resource or a service. This could be, for example, a kernel object. This could be a subsystem for Mach or other similar things. So usually you get access to this via calling a kernel API. And the kernel API then gives us this port enabled to control the specific resource or the service. And by having access to this port in our IPC table, it basically means we are allowed to have access to that resource. and usually these APIs that give us this port are performing all the security checks. There's very few runtime security checks for this kind of stuff in Mach, because usually the idea is the moment a task has access to a port, they should have all the rights on it. Of course, this has been abused in exploits, so for various ports, Apple has nowadays changed it a little bit. But the basic idea in Mach was that the moment you have access to the port, you should be the controller. Yeah, and that also means that for many types of ports, the moment they fall into the hand of a low privileged process, there's no further protection. Okay, as I said, one of the possibilities is that it's a kernel object. So the kernel object types are basically defined in this file ipc_kobject.h, and they used to be a define, but nowadays they are like an enum. And you can see there's a lot of these possible kernel object types defined here. And what you need to know here is that there's just like not a complete list, so there are more. And also usually when you look at the type, it will give away what a port internally looks like, the structure. For example, when it's a thread control port or a task control port, then it will point to the k-object pointer will point to a struct thread or a struct task. In this case here, it will point to a struct host, and so on. For IOKit objects, it will actually point to a C++ object that represents the specific IOKit object in kernel land. File ports are a little bit special because they are actually not pointing back to a Mach data structure. File ports actually point to a BSD style file glob structure. So that points into a data structure coming from the BSD part of the kernel. So let's get to some of the APIs. So here you can see there's the Mach host self API. This basically gives you access to the system-wide host port. So the result is basically that you have suddenly a host port in your IPC table, and you have a port name for that, and you can access it. Same for Mach task self. This gives you access to your own task port. Mach thread self gives you access to your own thread port. Keep in mind, internally there's a data structure in the kernel that points to either struct task or a struct thread or a struct host basically. So there are other more complicated API, for example host get clock service. This is something that gives you access to a clock port. And then you have host get IO master. This is a special API that gives you access to a special port that is a master device port. And this is basically one of the important ports if you want to play around with the IOKit API, because a lot of the IOKit API does not need an IOKit object to deal with, but it needs a master device port to be able to talk to IOKit. A lot of other IOKit functions, they will just take an IOKit object, a kernel object of type IOKit something. But in this case, sometimes they need the master device port. So host processor sets is basically an API that is a little bit different from the previous ones because it requires that you give it a host priv port. A host priv port is basically similar to a host port, but the fact that you have access to a host priv port means something like you are the root user in the terms of the Mach part of the kernel. So that means you're a privileged user and you can access privileged API, and host processor sets basically gives you back ports to control the processor sets of this of the system. Yeah, and it is usually the same logic everywhere. The moment you get access to a certain port, there are other API that you can now call. For example, when you have the host port, you can now call host API. When you have task, then you can call task API. Processor sets, then you can basically execute API meant for specific processor sets. Yes, so that was the APIs that exist. Of course, there are many such APIs. Let's look at the writes that a port can or that you can have on a port. And the first write is the so-called send write. A send write means whoever has it is allowed to send Mach messages to that specific port. A receive write is giving you the right to actually receive messages on a port. There can only be one receiver, so only one task has the receive right, and it means kind of they are the owner of this port, and yeah, that's it. Send once is a special send write that can only be used one time. The idea here is that sometimes, for example, when you have an API, you only want to be able to send one reply. Then you basically just have a send once write to basically the reply port so that you can reply only one time. The port set is a collection of writes, we ignore this. Then the dead name is a special write that is basically a placeholder in our IPC table in case something goes wrong with the ports that are inside our IPC table. For example, when you have a send write but the receiver dies, then our IPC entry will be modified to have a dead name in it. And the same thing is true when you have a send once write and you have already used your one-time sending, then this will internally be marked as a dead name in the IPC table. Yeah, that's basically the whole magic here. So all that said, now there's a kind of different usage for IPC ports, and this is by basically for communicating between two entities. And in order to do something like this, you need a port that can receive messages and so on. And there's API, of course, to create such a port. And one of these APIs that is easiest to use is called Mach_port_allocate. And here you can see how you would use it. You basically provided the current task. You provide it with the rights that you want to have, which would be the receive right, because you create the port for yourself and you want to be the receiver. So you immediately give you the receive right. And you need the port you need the port name to be able to use that port. And so you specify in this case that it's written into the my port variable. And then from that moment on, you can use this port that is referenced via the handle in my port by just calling any port API and specifying this port name basically. So one thing that's important here is to realize that even if you forget this port name number there, it is still inside your IPC table, and so you still have access to it even if you accidentally lose this number. So the moment you guess this number right or brute force this number, you would then be able to send a message to this again. And this is important to realize because this is also one of the reasons why the gen count is a security feature, because one of the possible attacks in userland for cross application or cross task exploits is to basically get a valid port name in another process and make them send a message to you, and as we will learn later, these messages can forward these ports to you, and then you can steal these ports theoretically. Yes, so that's all we have for today about Mach ports. Of course, the next chapter will be to understand what Mach messages are, which we basically will sending via these ports. But this is not for today. See you tomorrow for the next door in the Advent calendar.